All right, so we're back and we want to kind of dive properly into this Ford-Fulkerson algorithm. So I've left out some of the details intentionally so that we can kind of play the game a little bit, and then we'll come back to some of the kind of technicalities. So in the last video, we chatted about this notion of augmentation, which was basically you give me a flow, I can build a residual network, I can find a path, and then I can actually do this augmentation. That's kind of viewed as like the middle step in this overall algorithm. That's the idea that we're going to run over and over and over and over again. What we want to properly do then is basically initialize this thing and then begin letting this process snowball out of control. So that's what we're going to play here, is that we're going to kind of see all of the little pieces come into play. We'll have our first move, our second move, our third move, ideally ending up at some type of optimal flow at the end. So we're still going to be dealing with our cool little Canadian cities map, and we're going to have some movement of goods. So we at least kind of know what the final answer is going to be. So we're going to try really hard to get this thing up to a flow of 23. What we want to do though is we're going to start this process somewhere. So basically initialize everything as possibly being zeroed out, which is the least interesting flow network that's ever been constructed, in that we have all of this potential and we're not using any of it. So everything is currently zeroed out. So from Vancouver, we're not sending anything. Winnipeg is not receiving anything. But we do need a starting place, so that's where we're going to start. So once we have that, we're then going to take that flow and build the corresponding residual network. So the residual network is keeping track of things that we're currently doing, which is nothing right now, and then keeping track of additional movement that we could possibly get. So those are going to be those little green edges. So the green edges are achieved by taking my overall capacity and subtracting off what my current flow happens to be. So that first path, you can see, we're doing 0 of 16. So we have potentially 16 more that we could push through that. Same thing down below. I'm currently at 0 of 13. So I could pump 13 things. And then I could do that the entire way. So when I build up the residual network, it's going to look something like that. I officially did not draw in all of the zeros because they are obnoxious to look at. I drew one of them and I was like, I'm not doing that anymore because it's going to make my system look utterly awful. And that's actually pretty common, is that we're not going to draw the zeros because they're not going to be useful to take. They're not going to give me anything new. So we typically just avoid all of them. But formally, you would have a bunch of zeros of what we're currently doing. So the green 16s and the green 13s and all of those other numbers are then going to represent potential gains that we could have through this system. So now the question simply boils down, can I find a path? And that's where this process gets really fun. So in later sections, we're going to chat about different implementations and kind of swap out different pathfinding algorithms and see how that changes the game here. But for right now, it's simply going to be a question of, can we find a path? And if a path exists, then we know that we can augment and actually improve things. How you choose the path, though, is kind of fun. So here we might just try to run like just a straight greedy algorithm. So right out of S, the best case scenario is going to be to go up to V1. And then you're going to see, okay, well, from here, my best case scenario is going to be to go across to V3. And then I'm going to compare the 9 and the 20, which is then going to send me down to the T. So we do have a path, which is hopefully easy to see because that was our first move, and we better have a path right away. And we have a pretty decent path. So this thing is going to be limited by this value of 12. So what my implementation or my augmentation is going to improve is that it's going to click up by a value of 12. So if we want to introduce some notation, I'm going to say that this is my original flow F naught. The little path that we're going to see down below is going to be viewed as path F naught prime, and that is currently limited by a value of 12. So what that means for us is that as I go across this whole process, when I do the augmentation, everything that's going to be along that path is actually going to uptick by a value of 12. Everything else is actually not going to change, and then we're going to rinse and repeat this process over and over and over and over again. So let's go ahead and do that. So I have a 12 there initially. So let's cycle that over. I'm actually going to change colors really quick. I realized that the earlier ones that I had, I did all of those in yellow. So when I swap back to some of the later ones, I want to keep the colors somewhat in check. So I'm going to yellow that thing out, and I'm going to change this to the fancy mac and cheese color. And it's going to say, hey, that's a 12 bounded by that. All right, cool. So that's going to pop up to a 12. That's going to pop up to a 12. That's going to pop up to a 12. And everything else is still going to be zeroed out. Neat. So that's going to be one iteration of this little algorithm. You're going to start with a flow, which is zeroed out. You're going to build the residual network. You're going to find a path in that residual network, and then you're going to do the augmentation. Rinse, repeat, over and over and over and over again. So this one will actually terminate in a couple extra moves, so we'll see all those pieces come into play. So now we have this new flow, which I'm going to call, let's say, F1. So we had initial flow, F0. Here we have F1, then theoretically we'll have F2, and so on and so forth. So what I want to do next is I want to build the corresponding residual network for it, which again is keeping track of additional movement as well as what we're currently doing. So if we go and do that, well, last time we added in 12 across that yellow path. So now my bounds on these ones across the top are going to change. So I'm using 12 of the 16, so that means I could only possibly add 4 more. The middle one from V1 to V3, that one was maxed out, so I'm not going to draw that 0 transition. And then this far right one is going to be capped at 20. So if I'm using 12 of the 20, I have 8 more goods that I could send across. Everything else is identical because I didn't change or use those things at all. So I'm still going to have 4 in that direction. I'm still going to have 13. I'm still going to have a 9. I'm still going to have a 7. And I'm still 14 and a 4. And then in red, I'm going to keep track of what I did in the last move. This is the idea of in case I don't want to do it. Maybe I made a bad choice. So here I would possibly send 12 back. Here I would send 12 back on that route, and here I could send 12 back on that thing. So then it becomes this question of, can I find a path? If I can find a path, then I know that I can actually improve things. And I missed a value down on the bottom. All right, so if I can find a path, then I know that I can improve things. If I can't find a path, then I'm done, and I'm going to return whatever the previous flow was back to the user. So if I try to do this greedily again, I can go straight down to here, because 13 is currently winning. And then if I go here, 14 is definitely best. And if I go up, there's going to be a 7. So technically the greedy algorithm, if I straight up just applied it, the 12 backwards would actually win. But if I did the 12 backwards, then I'd be at V1 and I'd have to go all the way back to my source. So that's not going to be optimal. Same thing if I took the 9. If I took the 9 back, I would then end up ultimately ending back at my source. So really what this greedy algorithm should take is that 8 route into my final end. If you look at that little path, this augmenting path, it is limited by, whoa, not erasing. Well, then it'd be super duper limited. So it's limited by this value of 7. So I'm going to write that as this. So this augmenting path has a capacity of 7. And then I'm going to do that process of increasing everything by a 7. I'm only using the green edges. So here I'm still just pumping in extra goods wherever there's spots to be had. And then eventually we'll see if we have to move and shake things around. So anything that's along that blue path is going to go up by a 7. So this one increases by a 7. This one increases by a 7. This one increases by a 7. And that top right currently had 12. So when I have 7 more added to it, it's then going to pop up to a 19. And everything else is then going to stay put. So that's going to stay at 12. That's going to stay at 12. And then the other ones are still going to be all zeroed out. So zeros and zeros and zeros. So that just created a new flow, which I'm going to call F2. It currently has a value of 19 because you can see there's 19 things leaving. So the 12 and the 7. And we also are receiving 19 on the back end. Also, everything else in the middle is technically squared up because that inflow does equal outflow. But we know that we can get to 23, so we have to keep on marching along. So what we're going to do is we're going to then build another residual network for this thing. Again, we're going to have more and more red things emerging as we have more and more things in our network. Find a path, rinse, repeat again. So you'll see those big moves. So we're doing the same thing over and over. So flow, residual network, path, augmentation. Flow, residual network, path, augmentation. Flow, residual network. Okay, so that's what we need to do next. We're going to have to build that thing up. And try to see if I can see my original graph. So in green, I'm going to keep track of all of the extra goods I could get. So I'm currently sending 12 of 16 here, so I could pump 4 more. I'm currently sending 7 of 13, so I could theoretically pump, what, 6 more? Across the middle, I'm currently doing 7 of 14, so I could theoretically do what? I could do 7 more across that bottom there. What else? We have 0 of 4, so I could pump 4 more there. Across this one, I could pump 1 extra because I'm currently doing 19 of 20. I could send 9 back if I wanted. I really, really don't want to use that one because we know that it's bad. But big picture, I wouldn't necessarily know this if this was a network of 20,000 things. And up here, I could send 4 up to the top if I wanted. All right, so now the red ones are going to keep track of what we're currently doing. So the 12 could come back to the beginning. I could send 7 back to the beginning. I could send 7 back to the beginning there. I could send 7 back here. 4 is not. I could send 19 back, and I could send 12 back. So those red ones are always going to be constructed by just taking whatever your current flow is and then switching the order of those arrows. So the green ones are going to point in the same direction that your flow is doing. The red ones, then you can think about as being like a negative value. So it's going to go in reverse. And there's actually different ways you could implement that. You could actually just have the plus and minuses and then keep all of the directionality the same. I like explicitly drawing the arrows backwards because it feels right. But then I got to remember that they're going to have a negative value corresponding to them. All right, so now we need to find a path. And if you look at this, you can hopefully find a path right along the bottom. If you tried some type of greedy algorithm, again, you'd say, okay, grab the 6, grab the 7, grab the 4, and then you're into your final spot. Later, we'll see that greedy is not necessarily always the best. And you kind of can already realize it, is that in a flow problem, we're very much so limited by things that are going to happen later. So if I have 20 and 20 and 20 and 2, I'm then going to be limited by that last little value. Same thing technically happened here, is that everything looked great. It was a 6 and a 7, and then wham, I went all the way down into a 4 at the end. So greedy is nice because it's easy to implement. It's going to have some issues, but it's pretty nice. It's not necessarily going to be as good as like a Dijkstra's or something that we're going to actually try to find optimal, but it runs significantly faster. So we'll save some of those discussion points for the actual implementation because it's fun to see how many iterations it's going to take depending on different processes. All right, so everything along that purple route is going to be improved by a factor or by a 4. So I previously was at 7, so 7 is going to pop up to 11. That 7 is also going to pop up to an 11. That 0 is then going to pop up to a 4, and everything else is going to maintain course. I need to be fancy with my colors and keep track of when things changed. So the yellow ones changed first, which is why I went back and changed the colors. The blue ones changed second, and then the purple ones changed third, and the black ones were never affected. I really didn't care about them at all. All right, so we just created a new flow. This was technically flow 3. I guess I should say this previous path that we constructed was capped at a value of 4. So then we improved our flow by a 4. So now we're technically at the value of 23, which we've at least thought is optimal. But now I want to see how that would actually be recognized by this algorithm. So what's going to occur in the next move is I'm going to again build our residual network, just like we've done. So again, process is flow, residual network, path, augmentation. Flow, residual network, path, augmentation. Flow, residual network, path, augmentation. All right, so now we're at the flow. Now we got to build a residual network for that. And then if a path exists, then we keep going. If we can't find a path, then the previous thing is in fact optimal. All right, so it's going to look a lot like the previous one. So I'm going to have a 4 there, and I'm going to have a 1 there, and I'm going to have a 4 here, and I'm going to have a 9 there because those ones weren't used last time. And then the things across the bottom are going to change. So I previously had 6, but now I'm down to a 2. So I'm using 11 of 13. Across the middle, I previously was at 7, and now I'm using 4 of them. So I'm going to drop down to a capacity of 3. Up to the top, I was at 4, but I'm using all 4 of them. So now I'm down to a 0. So I think that's all of the green things. And then becomes the question of let's add in all of the red stuff. So this would be possibly moving in case I need to. right, so 4, that's a 7. All right, so now I have to do some arithmetic. So here I have 11, and here I also have an 11. All right, so that's my final residual network. And the idea here is that if you stare at this long enough, you're going to realize that there's actually no path from the source into the sink. This one's actually a little bit easier to look at the final location. The only way to get to the final location is from V3, and there's no way into V3. If you tried to think about this as running some type of greedy algorithm, you'd be like, okay, the 4, well, the 4 just has the 12, which would bring me back. So that's no good. And then you're like, okay, the 2, hooray. Now what happens? The 2 would take the 3. Well, there's no way out of there, so that doesn't work. So then you'd be like, okay, 2, all right, up to 4. Well, that's no good because that's going to bring me back to there. And you very quickly see that it's not going to work. There's no way into this V3, which means there's no way into the T. So the idea is that there is no path here. So the moment you can't find a path, that means that your previous flow is then maximal, which is really cool. And that's actually going to become your stopping place for this algorithm. So you have this overall back and forth, back and forth, back and forth, back and forth until you can't improve things at all. So if you go back into the notes, you'll see that I have a couple different runs of these. And I want to just quickly go over the second example there because it actually makes use of the red path. If you look at this one, we never used any of the red ones. So you might be like, why do we ever use these red things? They seem like a lot of obnoxious bookkeeping that we never actually needed. Well, if you go into them and you can see this particular run, you kind of identify why the red ones are necessary. Basically, the red paths are going to be there if we ever chose poorly. So starting off this game again, we have my original network. I'm going to zero out my flow just because that becomes a convenient starting place. We're then going to build the corresponding residual network, which looks the same as my original network. And here I chose this really poor path that went down to V2, up to V1, and then down to that little location of T. If you stare at that one long enough, you can kind of see where this is then going to become problematic in that going from S to V1, I have the potential of shoving 16 things down that route. However, if I take 4 and bring them up from the bottom, I'm eating into that 12. So I initially have the 16 funneled down to a 12. Well, now it's going to be further funneled down into an 8. So it feels really restrictive at that point, which it definitely is. So if you run this, so you find that path, that yellow one, and then you augment and you add 4s everywhere. You're like, sweet, now I have 4s. Then you go back to your little network and you build your corresponding residual network. And now you're going to try to take that top route as much as you can. Well, you already ate into that 12. So the only way you're going to get across that top is with 8 goods. So then you do the augmentation and add 8s all the way across. And here's where you can start to see the glaring problem that's going to emerge is you still have 8 extra things that you could shove into V1, but you have nowhere for those to go because we're bringing 4 up from V2 and then we're sending them across where you're like, hey, you got all this space down here. Why did you send them that way? Why did you send your junk up towards us? So then the question becomes, okay, how do we actually remedy that problem? Well, if you went to your next move and you tried to send the things across the bottom, you'd have those 9 run across the bottom into the 14. It hits the capacity at a 7. So then you do the augmentation, and now you're at this little network. And then when I build the residual network for it, you can see that this greedy algorithm is actually going to gravitate towards grabbing that red edge, in that it's going to jump up and then come down on that red route. And then it's going to run across the bottom. And what that does for us in the augmentation is that it's going to do the plus minus game, and that I'm going to add 4 to all of those green edges. And then the red edge is actually going to have a subtraction of 2, which then over here is then going to fix that idea that I sent 4 up. I'm going to redirect those things down across the bottom, and everything does get fixed up very, very nicely. So the red edges are necessary. I typically don't bring them out until absolutely necessary at the very end. They become less useful if you choose your paths cleverly, but they do need to be in your system to possibly undo some unfortunate moves that you may have made along the way. So if you funneled some goods into something and then created some type of choke point, they're going to then create your ability to undo that action before. So they're nice, they're kind of cool. A lot of times when students implement their, hand-drawn versions of them, they never make use of the red ones. So they sometimes question, like, why do I even need these things? They exist in case you choose a bad path. And if you just let this thing randomly choose paths or use some greedy algorithm, there will be the potential that bad paths existed, and you need to kind of claw your way back out of that hole. So on the video I ran through this one, I had that as my second example. I technically have another third example up on top, which is hopefully very similar to the one that I just worked out before, and that I went across the top. I did the zigzag thing, and then I ran across the bottom. So that one is this kind of greedy approach. In some activities, you're going to be running through a variety of other examples of these as well. So you can kind of get your hands dirty by building these things. Once you do like 1 or 2 clicks through them, then the whole process does flow very nicely and it becomes pretty enjoyable. Enjoy, have fun.